Hi, this is Scott Wilkinson, host of Home Theater Geeks. In episode 122, I chat with Matt Hirsch and Gordon Wetzstein about their new multi-view 3D flat panel technology that they're developing at the MIT Media Lab. So stay tuned.
Netcasts you love.
From people you trust.
This is TWiT.
Bandwidth for Home Theater Geeks is provided by Cachefly at CACHEFLY.com.
This is Home Theater Geeks with Scott Wilkinson, recorded July 30th, 2012. Episode 122, Glasses-Free 3D at MIT. This episode of Home Theater Geeks is brought to you by Netflix. Watch thousands of TV episodes and movies on your PC, Mac, iPad, iPhone, or TV instantly. All streamed directly to you, saving you time, money, and hassle. For your free 30-day trial, go to netflix.com/twit. Hey there, Scott Wilkinson here, online editor of HomeTheater.com. This week's guest geeks are Matt Hirsch and Gordon Wetzstein. Matt's a PhD student, and Gordon is a postdoc at the MIT Media Lab, where they do all kinds of cool futuristic stuff. Hey, Matt and Gordon, welcome to the show.
Hi, Scott. Thanks so much for having us.
Now, both of you are on the same Skype feed, on the same computer, because we were having a little trouble. The MIT Media Lab is at the bleeding edge of things, so that might have been causing a little interference with one of the Skypes. But we got you both here now, and that's very good. Anybody who is logged into the chat room at irc.twit.tv or watching the show live at live.twit.tv can post questions for Matt and Gordon, and I'll pass along as many as I can. So the reason that I wanted to have you guys on the show is that you're working on what to me seems like a super cool 3D display that doesn't use glasses, which is the bane of everybody, and achieves a better sense of 3D without the weirdness of auto-stereoscopic displays that I've seen so far. Give us an overview of the system that you're working on.
Okay, Scott. Yeah, well, I think to start with our vision of where 3D should go, we'd love to live in this future where displays function more like a window than a flat billboard in space. We'd like to be able to walk up to a screen and look around an object in 3D and really get to the point where we have a hard time telling if that's an object on a screen or if it's a real object on a table. So we've been working on basically adding computation to 3D displays for the last couple of years here at the lab. And you can think about that as, if you take a picture with your digital camera or a video with your home movie camera, they record data in a compressed way. They get rid of a lot of the redundancies, and they sort of store a much smaller file than if you just recorded every pixel of every point in the world. So
right, which would be huge. It would be a huge amount of data.
Exactly. And with our displays, we've been trying to do that for the output side for 3D. So we've been trying to make these 3D displays that basically solve a computational problem in order to create a set of patterns to put on some screens in space so that we can basically send a lot less data to the screen and make 3D displays that are high resolution and high frame rate practical today. And instead of using some very futuristic holographic technology in how many years.
Well, that'll happen at some point, but in the meantime, I would love to have a glasses-free 3D display that was very high resolution, high brightness, good contrast ratio. Gordon, if I read your papers and stuff correctly, which are pretty technical, you're really taking two different approaches here, or combining two different approaches, I should say. One is with the computational or the signal processing, as Matt was referring to, and the other is with some sort of new application of optical layers and technologies and so on.
That's right. So I would just briefly like to mention how glasses-free 3D is an amazing technology, but there's a couple of ways of trying to achieve that, or of achieving this. So the thing is that really smart people have looked at this in the past, and already about 100 years ago, Gabriel Lippmann, for instance, who received a Nobel Prize for the invention of color photography, has invented methods of doing that, and there are commercial displays available today. But all of these have major shortcomings. They're low resolution, you can move around only a little bit, but the main limitation is basically the bandwidth that's required for a high-quality 3D display. If you think about just the data that needs to be processed, we're talking about terabytes per second that need to be processed in order to show you an image. If you're talking about something like HD resolution in 2D for many, many, many different viewpoints, so you can walk around the display and see different perspectives of a 3D scene. Right. Now, what we're trying to achieve is this compression, which is just like JPEG or MPEG for videos. Instead of storing every single pixel at every single time frame, you just have this compressed representation of the scene. And if you look at it as a human observer, it looks just fine. You don't really see a difference. And the way we achieve that is by basically combining optical design and computational processing. And that's something that people haven't been able to do in the past because they just didn't have the computational power that we have today. So today we have like super fast GPUs, all the gaming cards that people use for computer games, and we can really run sophisticated mathematical algorithms at a really high speed on these graphics cards, and in combination with new optical designs, we can achieve a better quality than what everybody could do with just the optical design. So that's the essence of all the work we've been doing for the last 2 years, and we've basically come up with different ways of achieving glasses-free 3D that differ in what people have been using in the past.
Now, Lawndog, I'm sorry, go ahead.
So maybe Matt can just give us the basic gist of the optical designs.
Well, so there are a couple things, I would say, trends in consumer-level electro-optics, so things like LCD panels that we've really been taking advantage of. One of those trends is high speed. So we mentioned that we're using compression, and one of the key methods that allows us to use compression is to combine a bunch of frames that the display can show at a very high rate together in the human eye. So we're kind of taking advantage of the way the visual system works in order to show these compressed 3D images. And so the way we're able to do that with current technology is to take a couple of these LCD panels that were designed for shutter glasses 3D that can run at up to 120 hertz or even faster. And then 240
is also not unheard of. Certainly, there are many sets available with that kind of refresh rate as well.
That's true. Although if you take a high-speed camera and film one of those 240 hertz displays, you may find that they're not actually running at the rate you... True.
They call it 240, but it's really 120 with backlight flashing.
Yeah. So for our stuff to work, we really need to be able to send a new frame at every one of those steps. And so the best we found commercially is really about 120 that you can drive with a sort of an off-the-shelf video card. Now, if you want to go build your own display controller, you can do a little better. But we haven't gone down that path yet. So that's one trend, is this very high-speed display. Another trend that's been kind of being explored in some areas of the 3D space are these directional backlights. So if you look at like 3M, for example, I don't know if they actually had a product with that, but in their research lab, we got a chance to go over to Minnesota last February and take a look at some of the stuff they were doing out there. And you can see they have these directional backlight films. So they do these big roll-to-roll printing processes where they can create these very precise plastic micro lens structures, and they can form them in a specific way so that when you light a backlight from one side, the rays come out in one direction, and when you light the backlight from the other side, they come out in the other direction. And by doing this, they're directing one view to one eye and another view to the other eye. But
instead of what's typically called a parallax barrier, which is where there are little actual ribs in the display. This is, I think, a more conventional autostereoscopic display. that sort of direct the light in one way or another. Is that instead of that?
Yeah, so that would be instead of that, right? And in our work, we kind of started by generalizing those parallax barrier patterns that you described. But this other approach, this directional backlight approach, has been really kind of just starting to gain foothold. And so in our latest work, which you can see behind me back there, we've been able to exploit some of that work that's been done in directional backlighting in order to improve what you can do with just a bunch of layered LCD devices. Maybe at this point it'd be a good time to show some of the video of our...
So I would just like to add something. So we really have been exploring 3 different paths in this optical design. One, which is probably the most intuitive one, is just stacking up multiple LCD displays on top of each other. So imagine you take your TV or your computer monitor, you rip out all the electronics and the backlight, and what you end up with is the actual LCD panel, and you can see through it. So if you take multiple of these and stack those up, you actually get more degrees of freedom, and that allows you to create a 3D image. So that's the first step we tried, stacking up multiple LCDs on top of each other.
Before you go on, let me ask you a question about that. So you have how many layers typically?
So if you're talking about the minimum amount of layers is basically 2. So this is what most commercial devices do even today, even the Nintendo 3DS. Talking about the Nintendo 3DS, it has one LCD, then it has another LCD. You can turn that into a fully transparent mode, and you're just looking at a 2D display, or you can turn it on, and it basically shows you a slit pattern, which is an optical blocker. So that implements a parallax barrier, which is what you just mentioned, using an LCD. Now it becomes dimmer and lower resolution when it switches to the barrier mode. But this is
if you put stacked several of those, wouldn't that make it dimmer still?
Optically, it makes it a little bit dimmer, but what we found is that you get much more degrees of freedom. So you get a higher resolution, you get brighter images. If you can implement them optically efficiently, right? So
it turns out it's all about the right choice of patterns. If you use a pattern that's 50% dark, you're going to lose 50% of your light. But if you use a pattern that has a lot of transparency in it, then it turns out you can lose a lot less of your light.
Exactly. So say the Nintendo 3DS, for instance, you don't need to wear the glasses to see a 3D image, but you only get to see 2 different images, right? You see one image with your left eye, one with your right eye. So it's an autostereoscopic image. What we're exploring here is multi-view displays. So you see many, many different images being displayed in all different directions. So for the Nintendo 3DS that only has 2 different images, the parallax barriers basically eat about 50% of the light. And that's okay. You can just boost the backlight and you don't even notice that, right? But if you're talking about, say, 10, 20, or 50 different perspectives, it gets so dim that you don't see anything. So by stacking, say, 3 LCD layers, yes, it's darker optically than, say, using only 2 layers. But what you gain for multi-view display is much better, say, than simply using the parallax barriers.
And so then in that case, so if you stack up 3 or 4, so in other words, the number of layers you need determines the number of different views you can have?
Yes. There's no one-to-one mapping between, say, I want one more view to come out of the display, so I add one more layer. That's not the case. And here's where the compression comes in the game. So we have, say, in most of our displays, we use 3 or 4 LCD layers, and we display about 25 to 27 different viewpoints, both horizontally and vertically. So you have fewer pixels in the LCDs than you actually have rays coming out. And that's the compressive idea. So with fewer pixels, you get more viewpoints, right?
Gotcha. In fact, you've just answered a question from Dr. T in the chat room, who asked, is it only lateral 3D or can it do vertical 3D at the same time? In other words, to be able to look at the top and the bottom and see different perspectives as if you were going side to side as well.
Right, and actually we get the most benefit from our technology, from our work, when we try to create these both horizontal and vertical parallax displays. So there's just more data to compress, and so you can see a bigger difference between just using a standard heuristic pattern and using what we're proposing, which we call tensor display.
Okay, so Gordon, you were mentioning here's one factor of things is stacking several different LCD displays, or panels, I should say, on top of each other. And I assume that you boost the backlight in order to compensate for even a transparent LCD layer is going to lose some light going through it, right?
A bit, actually, yeah.
Yeah.
Okay, so that's one factor. You were outlining all of the different factors. So stacking several layers of LCD panel or actual crystal panel, not a full TV, is one aspect of it. Then please proceed.
Right. So we actually started out looking at these multi-layered displays by using simple transparencies. So what I hold in my hand here is a static prototype that, if you look at it from the side, it's a couple of sheets of plexiglass that have inkjet printed transparencies in between. If you use, say, a single backlight behind them, you can actually get a 3D impression of the object inside. So, we started out by just exploring new ways of creating 3D images. And then we built the LCD version. And as you said, we quickly realized that this may be something that may not be as commercially viable because it gets pretty dim. So we started to explore different dimensions. And that's the two other aspects that Matt actually already mentioned. So one is basically these directional backlights. And I just want to add something to this. So if you look at your laptop and you buy a LED display, for instance, in your MacBook or even in your TV. So what happens is you have an LCD display in there, and behind the LCD, there's basically a slab of plexiglass that's called a light guide. It's very thin, and it's edge lit. So there's basically a slab of plexiglass with LEDs on the side. And if you turn
around the edge, yeah.
Yeah, if you turn on these LEDs, the light bounces back and forth inside the light guide and basically re-illuminates your entire monitor, right? So these directional backlights are very similar, but instead of being just a slab of plexiglass, they have a specific shape. They're usually wedge-shaped. So what happens is you turn on one LED on one side, and it illuminates the entire display, but it only gets emitted from the display into a particular direction. So you turn on LED, you emit light everywhere on the monitor into a different direction. Now, what you can imagine is you turn on one LED at one time and show the image for the left eye, and then you turn on the other LED and show the image for the right eye, and you can switch between these, and optically they're just directed to your eyes. And that's the idea for directional backlights. You can make very thin displays, but you need really high-speed panels. So for stereo, you get away with two different patterns. So say you can do stereo because you still get a 60 hertz display. If you're talking about multi-view, you'd have to have thousands of hertz in your display to get these time sequential patterns. And here's where the compressive idea comes in again. We get away with much fewer time frames or much lower display refresh rate to achieve multi-view imaging. Right? And the last thing I want to mention, without taking too much time here, is this high speed. Remember, when the first cinematographic projectors were invented back maybe I think in the late 1800s, right? What they did is they had a roll of film that had individual frames of the video next to each other. And the video projector would play it back at 30 frames per second. And our eye perceptually averages over these frames. So we see a continuous video on the movie projector screen. So now imagine what happens if you show the same movie projector at 120 hertz. Now in this case, we still work at about 30 to say 60 frames per second, our visual perception. So if you show any patterns faster than that, we basically perceive multiple frames in short succession and perceptually average over them. And we can directly exploit that fact to build better 3D displays. So that's how we think about it, as an extension of these movie projectors that went from still photographs to moving images. And now we can use the same effect and higher speed displays to get better 3D displays as well. So it's these high-speed displays, directional backlights, and multiple stacked layers of LCDs. So we've explored all of these, and we can basically exploit them.
And combine them all together. Couple things come to mind real quick. One is I don't know about the very earliest days of cinema, but certainly the whole industry standardized on 24 frames per second rather than 30, as you said before. primarily, as far as I know, because that was the slowest speed they could get away with and still have a reasonably smooth sense of motion, because they wanted to conserve film as much as they possibly could. And as you probably know, people like James Cameron and Peter Jackson are now advocating shooting movies at higher frame rates, 48 and 60 frames per second, in order to make the motion smoother and crisper and have more motion detail. So that's a development that is sort of in congruence with what you guys are doing.
Right. So,
oh, well,
go right ahead.
No, I think that you see, I mean, just because we have the capability now to, produce these very high speed displays, that people are trying to figure out how to use it.
Right.
Manufacturer wants to sell you a new TV next year. They've already sold you the shutter glasses. What can you do with a 1,000 hertz display that you couldn't do with a 120 hertz display? And one of the answers I think is right here.
Yeah, exactly. Let me pose a couple of questions from the chat room while I've got them up here. Lawn Dog asks, as a concept, are you blending the idea of a 3D hologram and stereoscopic 3D? Is this a combination of those ideas?
Oh, sure. Well, so I guess this is in the realm of light field displays. If you want to sort of categorize the types of 3D displays, on the very, very far end, you have holography, which kind of exploits the wave nature of light and, creates features that are sub-wavelength for the illumination of the display, and can produce, basically, if you think about in the ray sense, can produce arbitrary rays in space. Now, that's very difficult to manufacture and very costly. And so we haven't seen a lot of commercial success with, devices that attempt to do that. Although we're now beginning to get to the point where we can manufacture an LCD, or at this scale, they call them spatial light modulators, in order to do that. But we're working really in the sort of ray space. So with a standard, LCD off the shelf, you don't have the diffractive power to really steer light. So you can just think about it as a hole that you can open and close, and you either see light through that hole or you don't. And in this space, we don't have arbitrary control over the rays we send out. We can send out rays in sort of fixed directions. And there've been a lot of work in light field displays. Most of the commercial 3D displays you see are really kind of light field displays if they're not stereo. And so our work really kind of just directs different views to different regions in space. And if we're just directing 2 views, that's stereo. If we're directing 27 views like our prototype, then that's multi-view. And people have a lot of different words for that, but call it multi-view 3D. But it's basically some discrete approximation to what a hologram is.
Yeah,
right.
And I would like to add that we're not intending to replace holography in the long distance. We think that holographic displays are basically the ultimate glasses-free 3D display. But growing up in the 90s and 80s, people have promised us holographic TVs in 5 years for decades. We have yet to see those, and part of the reason why that hasn't happened yet is because the fringe patterns you need to compute. Say, if you're talking about digital holograms, right? So analog holograms have been around for decades, and they're amazing. There's nothing that we could do that surpasses that quality. If you ever had a chance to see an analog hologram, it looks just like the real world. If you have a chance and you're in Boston, check out the MIT Museum. They have an exhibition on analog, and they also have some digital holograms. But creating the same quality for, say, digitally with a dynamic scene is very, very challenging even today. Because the optical design is so involved, you need to create optically structures that are so small that they create the diffraction that Matt was just talking about.
Yes, that.
And computationally, they're so involved that you need a supercomputer to run at for days and days to just compute one image, and that's something that we're trying to get rid of. We're basically proposing something that could be the next step instead of the step that will be there in 20 years or 30 years,
Gotcha. Yeah.
Looking at the near future here.
Now, you mentioned a bunch of different views, 27 different views in your prototype. Does that mean that one can move around the display and not see? In a typical auto stereo display, there are certain very narrow areas where you can stand, but they're next to each other. So you can stand right in the center and see 3D. You can move over a foot or so and see 3D again. But if you move over half a foot, your left eye is seeing the right image and vice versa, and things get really, really weird. Are you saying you've solved that problem?
Well, not exactly. So in those displays, really the only sort of true image is in the center, and all of those repeated copies of the image are actually sort of geometrically wrong. Now, our brain is pretty tolerant, so we kind of see those as also 3D. But with our solver, actually, only that central view right in front of the display gives you a correct 3D image. And as you go that, the illusion of 3D kind of breaks down, and you kind of see these different patterns on different layers. But the interesting thing there is that, what you really want to do is widen that view cone, right? You want to be able to have people sitting all around the display be able to see sort of perspective correct 3D no matter where they are. And actually, in our latest prototype, using these directional backlights, we've been able to really expand that field of view. I think we're at, 40 now?
40 degrees.
Yeah.
So maybe this is a great time to actually show what the display looks like, right?
Sure,
so
absolutely.
Send you guys a couple of clips. So if you just play the one that says results with fish or 3-layer, I think that should just show what you see when you look at the display. Okay.
John should be able to pull that up. That looks like the one.
Yeah, so what you're looking at here is basically the display prototype, and the camera basically moves around the display. Or in this case, we just rotated it.
Right.
So what's being shown at a really, really high speed are these time-changing patterns on all these different layers. So you have these 3 LCD layers, and they all show different patterns, and they're so fast that the human visual system averages over a couple of those, basically showing a smooth view. So maybe we can just play it again.
So here's the vertical parallax, by the way, you're asking. So yeah, horizontal, you can see as the camera moves left and right, you get to see around objects. You can see they occlude each other. They're specular effects. You can see. So we can get, basically simulate everything the real world is showing you.
Now, there was a moment there in that video where things weren't clear, that there was a lot of shimmery stuff going around. We'll see it again here, I think, in just a second. Here we see the fish, and the display is rotating slowly right and left, and you can see that it's occluding some things. Here we go with the sparkly stuff. What's that?
So the sparkly stuff is actually the magic, right? So what you're looking at, the magic that makes this display different to anything that's out there right now.
That's if you had a very fast eye or a short exposure eye. That's what you would see.
Right. So this is what, right? What a human observer sees. Let's just play it one final time, right?
Okay.
It is composed of 3 LCDs, and they run at a really high speed. So what you see is this, but what the LCDs actually show you are these patterns that don't make sense when you just look at them, right? Because now we actually use the high-speed camera to film what's being displayed on the LCDs, right? On the front layer, the middle layer, and the rear layer. So these patterns don't really correspond to any viewpoint. They're just automatically computed by this optimization algorithm that we proposed. And if you look at it as a human observer, you basically see this smooth view. So that's basically the compressed representation of this 3D scene, that the flickery stuff, right? But it exploits these limitations of the human visual system and the capabilities that are provided by the display in terms of high speed and multi-layer. So it already combines 2 of these concepts that we were mentioning before. And we can pull out one other clip which basically shows the actual prototype so that you can see what it does. So it's this prototype 3-layer clip. Let's just look at it.
Yeah.
So, sorry, what do we got here?
So this is the actual hardware. We're showing basically 3 LCD layers where the front 2 have been modified so that they're kind of see-through LCDs. Like we were mentioning, we took the backlight off and actually stripped off the polarizer that normally sits on an LCD and replaced it with a clear one that you can just look through.
Mm-hmm. Yeah, okay. I see the 3 LCDs, layer 1, layer 2, layer 3.
So that's one mode that our prototype works in.
So that's basically the display that you just saw with the fish on it, right? And then
right.
you saw the patterns that are being displayed on each of the layers, basically.
Right.
Now that you notice is a pretty thick display.
It's not one of these super thin displays that people want.
Right. So if you want to take a look at the next hardware clip, what was that one called?
It's called Prototype Directional Backlight, I think.
Yeah. Okay. So here's sort of the manufacturing process, and we get to the directional backlight version, and you notice that this one actually can be very thin. So what we've got is a front layer, one of those clear LCDs again, on top of this directional backlight, which we actually build based on another LCD panel with a lens array on top of it. And you'll notice that this prototype is actually just barely thicker than the monitor that we disassembled in order to build it. So we basically just added another LCD layer directly on top of those lenses.
Now that only has one LCD imaging layer?
It has 2 imaging layers, but one of them we kind of talk about as a directional backlight because it's an LCD combined with a lens sheet right on top of it. So you may be familiar with the sort of lenticular-based 3D displays. That's sort of a 2D lens array, sort of like a lenticular on top of an LCD panel, which is the most general directional backlight you can have. It's sort of a low-resolution display that can shoot rays in both different angles and from different positions. So it's a low-resolution light field display, and you can think about sort of what the algorithm is doing conceptually as when we stick another LCD panel in front of those lenses, it takes each spatial pixel, which went from like a whole lens down to the size of the LCD panel that's on the front of those lenses. So we're basically getting this angular variation from the directional backlight, which gives us a really nice wide field of view. And we're putting another LCD layer on top of it and sort of restoring the spatial resolution so we get a nice high resolution image at each viewpoint as well. And maybe we can just show the last video, which is
there's 2 more.
Oh, are there 2? Okay. But we'll show one more video, which is the T-Rex directional backlight one.
What's it called again?
Dino, the Dino.
Results Dino, I think.
Let's see if we can pull that one up here.
Yeah, so this one is now showing it in that directional backlight mode. You can see there's a little bit of an artifact where some of our lens edges are because we as an academic group don't have a budget to buy these super expensive lenses. But what's going on here is those same high-speed patterns are being showed, but this time on the right, they're being shown beneath a lenticular sheet. And so that pattern not only varies in time, but also in angle as the display is rotating. So when you combine those 2 optically, basically sticking the left-hand layer in front of the right-hand layer, you also get a nice high-res wide field of view image, which you can see here, with the advantage of the display actually being really thin again.
Wow. Snowman. Sorry, go ahead. I was going to say Snowman Sam in the chat room is asking, so is it the computational algorithms that you've designed that decide which layer needs to highlight to give the 3D effect? And we're talking about the multiple LCD layers now. Right.
So basically, the computational algorithm that we developed takes a 3D scene basically as the input, and what it outputs are these patterns that change over time. And they basically
on all 3 of the panels.
On all 3 of the panels simultaneously. And that's the same for the directional backlight. So what you just saw, the flickering patterns, that's what the optimization spits out automatically, basically.
Gotcha. Dr. T asks, do you process multiple frames, more like a video than a still? I'm not sure I quite understand that question.
Well, we can do light field videos. Actually, maybe this is a good time to plug our SIGGRAPH Emerging Technology show that we'll be attending just next week. And we'll be playing actual videos on that display.
Because what we've seen so far is only still images rotating around by virtue of the fact that you're rotating the actual display around.
But I think maybe what the question is getting at is saying, are we playing these images in sequence? And yes, basically each static scene, every still frame of multi-view imagery requires a series of time sort of video of these compressed frames to be shown at a very high rate. So we show this very short, 3-frame or 4-frame video clip at a very fast rate, at a high, refresh rate. Your eye will just sort of integrate that all together into one still frame, and that's what produces 3D imagery.
Okay. Now I'm starting to understand. So we're seeing 3 or 4 frames being shown at a very high rate in order to give the 3D effect and be able to look at it from different angles.
Yeah. So in that video I described, in our SIGGRAPH emerging technology demo where we're showing a video, every frame of that video is actually composed of 3 other frames or 4 other frames, right? So it's kind of a funny thing where maybe one analog that people are familiar with is time sequential color. So if you buy a DLP projector right now and put it in
with a single chip and a color wheel.
Exactly. And you'll see, if you move your hand in front of it quickly or if you move your eyes across the screen, you'll see this sort of rainbow effect. And that's because the projector is showing red, green, blue very quickly and your eyes integrating it together. So we're asking your eye to do the same thing for the patterns that our display shows, only instead of time sequential color or field sequential color, we're doing sort of field sequential 3D, if you want to call it that.
So will there be some sort of potential for an artifact akin to the rainbow artifact of single chip DLP?
Yeah, I suppose if your eye doesn't integrate those frames together the way the algorithm expected, then you won't see the correct image. So
right,
some flickering or yeah.
Dr. T in the chat room asked a little earlier. So each person in the room, regardless of where they are, within some limitation, should be able to see a different angle of the same scene.
Yes, that's correct. So basically, there's no viewer tracking or eye tracking in these displays. So as Matt and I are sitting in front of a computer screen right now, we would be able to each see a different perspective of the scene, but each of us would see 2 different images with the 2 different eyes. So it supports binocular disparity, which basically means you get 2 different images for the eyes. But it also supports motion parallax. So you can move around the display and always get the correct perspective. So that's something you don't get when you go to the movie theater today, where you wear the glasses because the person on the left in the movie theater sees the same stereo pair as the person on the very right. So you don't get these different perspectives.
Right. Well, this is absolutely fascinating. I've got more questions for you, but before we continue, I would like to take a moment to thank our sponsor for this episode, which is Netflix. Of course, Netflix provides streaming TV shows and movies, thousands of them, which you can stream instantly to your TV or your computer, your smartphone, your tablet, your Blu-ray player, your game console. Just about any consumer electronics device these days has a Netflix app, which lets you stream those thousands of TV episodes and movies directly to whatever display you happen to have. You can even start on one device and finish on another, and you have unlimited access for one low price. Netflix is even offering a 30-day free trial for those few of you who are not familiar with, who do not have Netflix already. You can simply go to netflix.com/twit and sign up for a free 30-day trial to check it out for yourself. And I do highly recommend it. That's netflix.com/twit. And we thank Netflix very much for their support of Home Theater Geeks and the entire TWiT network. Who knows? Maybe someday we'll have streaming 3D. This was a question I was going to ask you guys.
Ask that too.
Yes. Are you accepting in a standard 3D signal from, say, a 3D Blu-ray player or a 3D broadcast, something like that? Is that what's being input into your display?
Well, no, not exactly. I mean, in some sense, it's an extrapolation of that. Those signals, basically, the Blu-ray 3D is really just a stereo signal, so 2 views. The input to our algorithm are those 27 views that you get that you want the user to see in front of the screen. So,
so the source then will need to change in order to make this some sort of commercial product. I know it's not going to be a commercial product next week or next year. That we're talking in the several year time frame here, but just to take it to its logical conclusion, there would need to be a source device that supplied those 27 views or however many you end up with for the algorithm to do its thing and show you those 27 views on your display, right?
Exactly. So that's a very good point, actually. But so what we see today is, stereo is mainly standardized. There's, recommended standards out there. People use these to encode, your favorite movie on the Blu-ray DVD. You put it on the player, and it has it in there. There's no real standards for multi-view yet, because it's just not a technology that's, being commercialized today. However, there is a lot of technology also on the camera side that is simultaneously evolving, say, with the display technology. So we're looking at these displays, but other researchers, for instance, the folks at Lightro, are looking at the cameras that are basically a new generation of cameras that capture exactly the kind of data that we would need for our displays. What they do with it is you can take a picture. They make these cameras, a new kind of camera. You take a picture and you can refocus it after you took the picture in Photoshop, right? That's something that's normally impossible. What they capture, the kind of data they capture, could feed directly in our display. So what I'm saying is, although it's challenging to create these multi-view input data sets today, basically we just use a ray tracer to generate them synthetically. In the near future, all of this will come together with the capture side, with the rendering side, with the standardization of the whole pipeline. Basically, it's basically, stereo 3D is pretty much established as of now, and will still be evolving throughout the next couple of years. But after that, I think the next step will be multi-view, and that will have to be targeted from all different angles. And we're only looking at the display side right now.
Understood. Ken, one other question related to that is, would it be possible, you're probably not doing this now, but would it be possible to take a standard stereo view from a Blu-ray player and process it to provide those 27 or however many views you have synthetically?
I guess the answer is sort of, but it won't be pretty. I mean, it's kind of like saying, if I'm looking at, a scene from here, can I tell what it looks like over there? And to some extent, yeah, I mean, there's correlation there. And there's been a lot of work in computer vision on that kind of extrapolation, and then in paint where there are gaps. But we much prefer to just capture the data or render the data in the first place than trying to extrapolate from a stereo pair.
Right. It's kind of like if you buy a 3D TV in the store today, usually the TV will come with a mode, so you can turn on the option to convert an existing 2D movie into a stereo movie, right?
Yes.
So on the fly, it will generate these two different views. It won't be able to do that correctly because the data is just not in the video, but it does an okay job, and sometimes it looks all right, And I think that's the same as taking a stereo view and generating these multi-views from that. So it's a similar problem. It'll never be something that you want to go see the new Batman movie in the IMAX with, right? But
no, that's exactly true, and your analogy is perfect. In fact, that the 2D to 3D conversion on the fly in these 3D sets simply isn't very good, generally speaking. And so the same obviously would undoubtedly hold true with converting stereo 3D, but two images, two views to many views. I guess it would require enormous computational power. Now, you guys, as you've said, are doing ray tracing and computer animation. All the examples we saw were definitely computer animation. I wonder if you could do that, if you could back engineer a computer animated 3D movie, since the 3D data is inherent in the animation, as I understand it. And correct me if I'm wrong, but in an computer animated movie, each object has its own 3D data, so one could potentially extrapolate that data out pretty well.
Yeah, you certainly could. Although I think to give those guys credit for what they do, it's not as easy as just hitting a button that says render. There's a lot of artistic effect and sort of overpainting that are very 2D. In the same way you apply effects to a live action video. So although there's a lot more potential, I mean, the data exists and someone could go back and render it. I don't think it would be like a trivial, place 2 more cameras in the scene and hit render again and have the whole movie.
Yeah, I think we've seen, say, the first Toy Story movie reappear in 3D now, right? And that's possible because the data was there, right? But
although I think with some of those, they even just hire people to trace them the same way they do with live action and make it 3D. Yeah, it's so difficult to go back and re-render.
Really? Wow.
Well, you have to say that there's a lot of script writing and artistic storytelling in these 2D movies, or even in the stereo movies, for visual effects or real data. And if you just show the same virtual scene that was animated back then for a particular camera perspective, that may look completely off from a slightly different perspective, right? Because it's just, I mean, they wouldn't hire animators to make it look great from perspectives that are never shown in the movie in the first place, right? So maybe some of the data is there, but I think it requires a lot of more processing than just hitting the button, as you said.
Yeah. Gordon, I know that you have a hard time limit here, so anytime you need to leave, let me know. I'd like to continue for a few more minutes if that's okay. But if you need to split, that's cool.
Yeah, maybe a few more minutes. Yeah, I'll have to take the laptop, unfortunately, too. So.
Oh, you have to take the laptop, too? That's your laptop. Okay, well, if you can stick around a few more minutes, I sure do appreciate it. Let's see. A couple people have been talking in the chat room about the Lytros camera that you mentioned earlier, and how might we implement that? JC, for example, says true holographic photography would require a hemispherical set, a hemispherical shape studded with Lytros cameras.
Yes. So what you need is basically a camera array that is mounted around the entire scene. Just like if you ever saw the making of The Matrix, they had this bullet effect. So what they had is basically an array of cameras mounted around the actors, and they shot photos in succession with all these different cameras, and then they could generate this virtual view that never really existed, right? So that's the same. I mean, he's right, right? But so the Lytro camera is basically a camera, and I don't have a camera here right now, but imagine you have an SLR camera or any kind of camera. If you're talking about a Lytro camera, it has like a lens that is like this big, right? A main lens, and what you can do is you can actually move the viewpoint, but only over the size of the aperture, right? So it's very subtle changes you can actually generate. So it's basically like a tiny little camera array over the size of the aperture of your camera, right? So you can't extrapolate from that either. It's more like this big. So it's not very.
So I guess to sort of go right to the question there, I mean, you would need a hemisphere to capture the full 180 degrees. I guess, if you want to capture sort of a narrower view cone, at least in this very discrete ray-based framework that we're talking about, in the sense of light fields, you can capture as narrow a cone as you want. Just sort of it depends on the optical geometry that you set up, What's the field of view and what's the zoom length of your camera, basically.
So the Lytro camera would really work well for a tiny little object that is placed very close to the camera, because now you're talking about this camera array that's over the size of the aperture. And if you have a tiny little object right up to the camera, you're covering this 180-degree viewing hemisphere, right? But as soon as you have something that's far away, obviously that's not the case.
Not so much, yeah. One person in the chat room I noticed earlier asked, has Lytros been talking to you guys? Have you been talking to them?
Well, we've been talking to them. Actually, we're teaching a course together. The CTO of Lytro, Kurt Ackley, and some of us are teaching a course on computational photography at the SIGGRAPH conference, where we'll also demonstrate our display prototype next week. So if you happen to be in LA, come by SIGGRAPH and check it out. We're talking to them, but like our research areas are more orthogonal than they align, basically, right? For us, we're a small academic environment, and these guys are really trying to hit the big market there.
Right, right. What kind of computational requirements are we talking about here in terms of, this is another question in the chat room from NT Matter. I mean, can you express it in terms of megaflops or gigahertz or anything like that?
So I don't have a number right offhand, but I'll give you some sort of, well, I'll give you something that may give you an idea of where we're going. So
okay.
Right now we're solving these, each single frame in our tensor display is solved on a GPU. And one of the really big contributions of the work, and something Gordon in particular spent a huge amount of time working on, is mapping the very abstract mathematical concepts required to run this optimization algorithm to the graphics primitives that are already implemented at high speeds in a special purpose graphics processing unit. So basically, we can run this optimization that generates the patterns for the display using projective texture mapping and basically rendering different planes at different distances and using multi-view output buffers. So basically, there's this really convenient mapping to these primitives that are already implemented in hardware. And in particular, we're using a Quadro 7000 card, and which I think has something like 512 compute cores, and all of this is implemented in OpenGL. And something like a gigabyte of memory, and runs at a couple of gigahertz.
So basically, we're talking about a high-end gaming card.
High-end gaming card, and it can run that decomposition at very nice high resolution in about, I'd say, 30 seconds. So if you want to run it in real time, you need a very much reduced resolution, and we've experimented with that. And if you look online on the website down there, compressivedisplay.com, there's a video where we show a clip of someone running something in real time on one of these, but with a very reduced quality. But we, expect, as always, the computational hardware will, follow Moore's law, and this is a very parallelizable problem and very amenable to graphics processing units. So we have confidence that, the next 5 years we'll be running these things in real time at pretty high resolutions.
And what about frame rates? Are refresh rates? Are you using the standard 120 hertz in these panels, or are you pushing them harder than that?
Well, it's unfortunate, although the panel can, I think we talked to one of the panel manufacturers, and they said the liquid crystal can run at 180 hertz in these panels. But as I said at the beginning, we'd really need our own hardware, our own frame buffer hardware, basically, to drive them at that rate. So, as far as we know, the best we can do with sort of off-the-shelf GPUs is 120 hertz with this liquid crystal display we got. So we run it at that rate. If you have a faster panel, you can do better. You can sort of turn the quality slider up on the compression. And we've been talking to companies that make high-speed display devices. We call them spatial light modulators, such as Pixtronics, which was recently acquired by Qualcomm. These guys make a little MEMS shutter display, similar to the DLP shutter or DLP mirror you'd find in a projector. Only instead of being reflective, it's just a shutter that can open and close, be transparent or not. And those things can run at about 2 kilohertz, although they're just binary. So we're very excited about these future technologies that'll give us much higher speed displays.
Very cool. Very cool. Well, listen, I know, Gordon, you have to leave, so I will say thank you to Matt Hirsch and Gordon Wetzstein of MIT Media Lab for explaining this new 3D multi-view, not just stereo view, but multi-view 3D technology. And wish you the best of luck at your presentation and classes at SIGGRAPH next week here in Los Angeles, where I hope to come down and say hi personally.
Well, that'd be great.
Yeah, we hope you do, Scott. Thanks so much for having us.
Yeah,
on.
thank you.
You're very welcome, and thank you for being here. Of course, as they mentioned, you can go learn more about their technology that they're working on at compressivedisplay.com. And my online home, of course, is hometheater.com. And you can email me at scott@twit.tv. Next week, my guest geek is scheduled to be Kevin Wines, the image technology director at THX. And we're just going to sort of geek out on the future of display technologies. Not that we haven't been doing that today, but things like OLED and 4K and the things we're going to see probably a little sooner than the multi-view display that we've been talking about today. In any event, it should be a very fascinating discussion, and I do hope you will join me then. Until then, geek out.